Okay, so here's our prototype. As you can see, here are the internals of it. This is our second version of our PCB. We've made a couple of edits to our design that we couldn't make prior to getting the PCB in the mail. Here's a pull-up resistor that we have going to 3.3 volts instead of 5 volts where it usually was going to. We have a couple of things tied to 3.3 volts as well. So here's our older version of our PCB. As you can see, it's missing an external oscillator for our codec, as well as a trim pot for our LCD screen. Additionally, we added a reset button on our second prototype. This allowed us to have a similar functionality to our Nucleo development board, which allowed us, just in case we ran into any issues, we could reset the device. So here you can see reset. Okay, this is just a quick demonstration of our enclosure and how it has some grounding capabilities. So right now we have the back plate off, as you can see, and it's very noisy, as you can hear. There's our PCB on the inside. We're gonna just take the back plate and put it right on. And the Faraday cage it creates completely reduces the noise.
Right, so we'll be flashing our PCB using the SWD port. All right, and here we have the STM programmer. As we connected, you will see the registers. This already contains memory that we stored previously, we flashed. But yeah, this is a tool for us to check the registers itself when we're flashing it. I'm gonna disconnect from this, and I'm gonna go ahead and use the STM32Cube IDE to flash a new version of our code. There we go. There we go, and now we're in debugger connection with the STM32. Let's get rid of all these expressions, and let's go ahead and start a new live expression for our TX buffer, and let's start a new one for our audio RX buffer. And let's go ahead and run the program. Awesome. So right now, as you can see on the screen, we have the audio transmit buffer and the audio receive buffer. They're receiving bogus values, of course, because our pedal right now is not connected. We're using the SWD connection right now through our ST-Link V2. And yeah, and we want to show you guys a little bit of the run with the looper mode setup. As you can see, the position that we have at the moment is 7, which is the looper, and the looper state is supposed to change to 1 right now in order to jump into the record mode. And as you can see, we turn on the live when we're in the record mode. This is, recording obvious bogus values that we're receiving right now from our RX buffer. And let's open this RX buff. This is actually the buffer that we're going to receive when we're reading from the flash memory. And as you can see, it's reading all those values from the flash memory into the RX buff, and all set. The LCD does stop, but this is normal because we are in the while loop. What you're seeing at the moment right now, and why it keeps why it keeps receiving values, is because we're going on a loop on the playback. So we're actually reading all over again from the start memory to the end address of where we wrote to. Yep, and that's pretty much it.
Hello everyone, my name is Conterno. I am one of the computer engineers in this group that worked on the firmware for our audio guitar pedal. And the other engineer is Alejandro. And today I'm going to make a really quick overview of some important aspects of our code and what we want to show you here and what we implemented. To start off, let me just point out, here is the graphical user interface that we utilized for our configuration of pins, GPIO pins, DMA, timers, etc. Very, very nifty tool. It basically initializes stuff for you. And it also sets the labels as well in the initialization and configuration files. So here we have the latest version of our code. One of the things that I wanted to point out is the buffer size, right? So today I'm going to be talking about a little bit of the algorithms that we're using for our effects and the ping pong buffer that we're using for our input and output buffer data transmission with the codec. Here we have the handlers initialization, some private functions prototypes initialized by the MX software that we just saw. Here we have the LCD prototypes that we're using, the encoder interrupt routine, all the positions and stuff. I'm really not going to talk too much about the code structure and how it's done, the code base. I want to focus the most on our receive and transmit I2S DMA buffers. So as you can see, the buffer size that we're actually passing, the amount of data that we're actually passing to our DMA send and receive or receive transmit functions is actually 4. And the reason why we're doing this is because the way that our buffer is set up is for the ping pong buffer to use half of it, processing that half, and the other half is actually getting stored into. As I said, we're doing a mono output. So basically the summation of our right buffer is going to be equal to the left. And at the end of the day, it really doesn't matter because we're not really outputting anything through the left. So I also wanted to show you the do effects function. This is pretty much our driver function where we're doing most of the effects that we're doing. I made it so that it takes in the summation, and this summation is also done with a multiply with a dry wet. Our wet parameter is pretty much our dry wet mixer, which is pretty much how much do we want the effects in total that you can hear in the output. So basically it's a combination of both of them. This works pretty well for effects such as do pitch shift and reverb, and also works pretty well with the delay effect as well. Here we have our effects. Just wanted to point out the way that we're implementing that structure, that digital filter structure. Here we have the COM filters parallel to one another, and here we have the series of all pass filters. For the pitch shifter, we have high pass. It's kind of like a helper function that we're using for the pitch shift. These constant variables that we see over here are actually calculated using a biquad calculator. It's a website that we used. We just specify the cutoff frequency that we want and the sampling rate, and it'll immediately give us the coefficients that we need. I could go on to talk about the states of the compressor. Basically, the compressor works sample by sample basis. So every sample, if the sample is above a specific threshold, then it's going to go through this state of gain reduction, which is this release time and hold time. Basically, once it's going through the gain reduction, we jump into different states to check if the next sample is going to go above the threshold and so on and so forth. It goes back again into that cycle of gain reduction, hold time, release, and then go back again to the attack. And here we have our write memory, erase memory functions. And basically jumping through it really quickly, we made our own functions to basically facilitate the process of writing and erasing to the memory, setting the CS bit low because it's constantly high. And in order to transmit a write enabled instruction, this has to be done every single time we want to write to it. And similarly, we're waiting for a bit. Whenever the flash memory is writing something, we have to wait for that busy bit to clear. I wanted to show you guys as well the record function that we're using. This at the moment, it's working. We're actually inputting data into the flash memory, and we're actually able to read it back with the playback function. However, the playback function is reading it so quickly that the rate at which we're basically transferring this out into the codec is too quick for it to actually be a decent guitar signal. We actually just get a really fast playback of whatever we recorded. But in theory, it's working and has a proof of concept. It's there.
Okay, so here we got our prototype all plugged in. We have the input jack going to the guitar. And we've got the output jack going to the amplifier. We're just going to plug it in with the 9-volt power just to demonstrate the startup sequence on the LCD screen. So there you see we have it currently on the clean mode, and our true bypass foot switch does not allow the affected signal to pass through. As soon as we turn this on, we have our affected signal, so we have a reverb here. This middle knob controls the amount of reverb you hear. You can hear that's a very dry signal, and as you turn the knob up, you get a fully wet signal. A couple more things I want to demonstrate real quick are the volume knob. This controls the overall level of the circuit. And then here's our tone control, which will make the tone a bit darker as you turn it to the left. Next effect we have is delay. And this has the same functionality as the reverb, where the middle knob controls the level. Next effect up we have is the pipe setting. This is a comb filtering type effect that has a very metallic ringing sound. You can take it out of the mix as well. Next up we have a pitch shifter. And this will take the original pitch of my guitar, which sounds like this, and we can add in a secondary pitch to it as well. The middle knob controls the mix between the pitch shifted signal and the dry guitar signal, and the left knob controls the pitch itself. So it goes from very low to very high. We also implemented a type of chorus effect with this, where if you take the dry signal and blend it in with the affected signal and adjust the pitch shift down to a very similar frequency, it has a very warbly, like vinyl kind of a sound. Okay. Next effect up is our compressor. This is a very subtle effect to hear. We have an attack, sustain, and release control. And this essentially will just boost your guitar signal, so it's a bit louder than your clean tone. Okay. Now finally we have a distortion, and this can get very loud, but we have it implemented to have, this controls our amplitude, this controls our overall threshold, and this will control the mix of the dry with the wet as well. So here's our distortion. And we can go all the way back to clean, and this is again just similar to our true bypass signal. Pretty much the same thing, so that's about it.